instructions today. I'm going to be presenting my screen and let me know when you can see it. Are you able to see the screen?
No, ma'am.
No, ma'am.
No, ma'am.
No, ma'am.
Okay, now?
Yes,
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 ma'am.
ma'am.
yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay, good. Right. So, what is a instruction first of all? An instruction is simply an order, okay, that we give to the computer. So you remember we had talked about the different advantages of using a computer in the first class itself? Yes or no?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
So using a computer gives us a lot of advantages, but at the very basic level, a computer is still a dummy machine. Now, why do we call it as a dummy machine? We call it as a dummy machine because it has no intelligence of its own. That means if I tell my son to make me a cup of tea and he doesn't know it, I teach him, I give him instructions once, or let's say twice or thrice, right? He will eventually learn it. But the system never learns in its very basic form. A computer system never learns the instructions. That means each time it executes a particular task, it needs the instructions. Every time what it simply does is it doesn't memorize them, it doesn't learn from them, it simply reads an instruction, decodes what it means, and then it carries them forward. Okay, then it executes them. Is this okay? Right? So that is why we say that a computer is inherently a dummy machine. Okay, so the set of instructions that we give to it together are called a program. So you must already be writing some simple programs in C++ by now. Yes or no?
Yes,
Yes,
ma'am.
ma'am.
What are
Yes,
you
ma'am.
writing there? What are you writing there? So you are writing, each line there is a command to the computer. It's an instruction. Okay. But you remember I talked about different types of programming languages, high level programming languages, low level programming languages.
Yes, ma'am.
Yes or no?
Yes, ma'am.
If you
Yes,
go
ma'am.
and look at my earlier lectures, you'll find that we've already talked about different types of programming languages. The high level programming languages don't concern themselves with the basics of computer system. They don't work at a very low level, as in you don't, for instance, you as you're using C++, you know, you although I have told you in computer system architecture that all the information is stored in form of bits and a character is generally taken to be a byte of computer storage, still uh, you don't need to declare your storage or claim your storage in terms of the number of bits or bytes. What you generally do is you just go and write int and then the name of a variable, char, and the name of the variable that you want to use. Yes or no?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes,
Yes,
ma'am.
But
ma'am.
what happens when you say char and let's say x? Whenever you, there's somebody, let me just see who wants to join in. Kanushi Baveja. I think late for the second time, Kanushi? Yes or no? Okay. So, what happens when you write down a statement such as char x? Internally, a byte of storage in RAM is earmarked and its name is given as X. So whenever you refer to X, right, internally, we go to that memory address and whatever is written there, we fetch it. Is it okay? That is what happens when you try and access X there. Okay. Yes or no?
Yes.
Yes, ma'am. Yes, ma'am.
But you haven't had to do this all yourself. It is done for you automatically. However, it is not so if we were using assembly language or machine language. Okay, so in assembly language as well as in machine language, which are low level languages, we have to deal with the bits and bytes ourselves. Okay, we have to directly deal with the bits and bytes ourselves. And that is why these languages are known as, this is one of the reasons why these languages are known as low level programming languages. Okay.
Yes, ma'am.
Yes,
Right.
ma'am.
Right. Okay. So what we are going to see today is what is the format internally of the instructions that you are possibly using in C++ without even realizing that. Okay, so you write a simple statement such as x is equal to 2, okay, or x is equal to y. How is that? How does that take place? Let me just show you. So before I go on to this basic instruction format, let me just show you. So so suppose you've written something like this. Okay, suppose this is a statement in C++. Can you see this? Or is it
No,
too
ma'am.
small?
No, ma'am.
No,
No,
ma'am.
ma'am.
No, ma'am.
You can see this? Okay, okay, just give me a second.
No, ma'am.
Now you can see this?
Yes, ma'am. Yes,
Okay.
ma'am.
Suppose you wanted to execute this statement, sum is equal to a plus b. Okay, where sum a and b have already been declared as, let's say, integers, right? So internally, how will this instruction be processed? Let us please see. So initially, let us say sum already contains 0. Okay, so now what I want to do is, if I use a single address instructions, so there are different types of instructions. We will be going in detail about the different types of instructions wherein we use different number of addresses. Okay, what are these addresses? I'll be talking about. For the time being, you can understand that they refer to your memory variables or variables as you call them. Okay, so Now, please see what is happening here. See, if I want to do sum is equal to a plus b, okay. Now, internally, if I have only a single address instruction, what do I mean by this is that my computer is able to handle only, let's say, one variable at a time, okay. Then obviously you can see that there are three variables here, okay. So we cannot manipulate all of them together. So how will the execution of this simple instruction take place internally? When I say a plus b, it is further broken down into a set of these two statements. First is add a, okay. So suppose this is my main memory here. This is, let's say, a snapshot of my main memory. Okay. So here there is a variable a with the value 2. Suppose a has a value 2. Okay. So as I said, you have already declared a and b. Let's say it has the value. What should I put in? What value should I give to b?
3.
3.
Four could be.
Okay. And another variable we have said is, let's say, sum, right? Okay. Now, you will also see with the help of this example how this particular register AC that I told you about, how this is implicitly used. I told you one of the specialities, one of the distinct characteristics of using a accumulator register is that it is implied, okay, in most of the computations, since it is attached directly with the
Adder and logic circuit.
Adder and
adder
logic
and
circuit.
logic circuit of the ALU. Yes. So initially, let's say the value of AC is 0. Okay. Now this a plus b is broken into, since I can handle only one variable at a time, what I will do is I will break it into two parts. So what I'll say is I'll first say add a. Okay. Now when I say add a, obviously I mean add 2. Okay. But to where do I add 2? I have not said that. You see, I have not said that. Okay. So what will happen? It will automatically be added to AC. So this is what will happen internally. Clear?
Yes, ma'am.
Yes, ma'am.
So the value of AC will now become
2.
value of AC will now become
2.
2.
Excuse me, ma'am.
Yes, beta.
Ma'am, can you repeat this? Ma'am, I didn't understood.
Okay. See, suppose we have to perform this instruction in, let's say this is a C++ instruction, any high level instruction. Okay. So what we want to do is we want to add two variables A and B. We suppose that they're already declared, and this here you see, what here you see below this line is a snapshot of my memory where I've created these three variables, sum and A and B. Is this clear?
Yes, ma'am.
So in the program somewhere, they've already been assigned these values. Sum is equal to 0, A is equal to 2, B is equal to 3. Okay. Yes or no?
Yes, ma'am.
So now there is this statement, this is there in this instruction which needs to be executed. Okay, we are just going to see how this instruction will be executed. I'm just taking this as an example, and after this I will proceed to the technical format of the instructions and what all things, all the things that we have that are related to it that we have to discuss. Clear?
Okay, ma'am.
Now, how will this instruction be executed? So when I say sum is equal to A plus B, and I say that we have a one address format, okay? So what does that mean? That means that I can handle a single variable at a time. That means the architecture can handle only one memory address or one variable at a time, okay?
Okay, ma'am.
So in that case, this instruction itself will have to be broken into these three statements. Okay, so that is what I'm showing you how this will execute, right? So suppose I simply say add A first. Okay, I say add A. What happens? You remember the accumulator register?
Yes, ma'am.
We
Yes, ma'am.
said accumulator is implied. Yes. So initially, let's say accumulator also has 0. Okay, we are starting the operation, so accumulator has 0. So I'll simply say add A. Though I have not specified where to add A, it will automatically be added to accumulator. Okay.
Okay.
So you remember from our bus diagram, if I put it into the perspective, you remember whatever address of A variable is there. Let's say the address is 200 here. Let's say its address is 200. Okay. And this address is B is stored at some address. Let's say 350. And sum is stored at some address. $120 in the memory. Okay, this is a snapshot of the memory. Clear or not? Yes or
Yes,
no?
ma'am. Yes, ma'am.
These are the addresses and these are the variables. So when you go and declare A, suppose I write a statement like this in C++, int A is equal to 2. This is how you do it? Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So this gets created. This gets created. A 2-byte memory is reserved and its name is given as A. Yes. Let's say this 2-byte memory is reserved at address 200. And then this value 2, whatever you've given, is assigned to A. Yes or no?
Yes,
Yes,
ma'am.
Yes, ma'am.
So I can say that it creates a 2-byte box and puts in 2 there at this address 200. Yes or no?
Yes, ma'am.
Yes,
So
ma'am.
similarly,
Yes, ma'am.
it does the same for variables B and sum. Yes or no?
Yes, ma'am.
Good. Okay. Now, please see, we already have these three variables in the main memory. Let's say at these three locations. And this is the accumulator register, which is inside the CPU. So if you remember, what will happen is when I say something like add A, okay, what will internally happen is address of A, which is 200, will be put in address register.
Yes, ma'am.
And then we will go to main memory, add this address 200, and whatever is stored there, which happens to be 2 in this case, is put into the data register.
Yes, ma'am.
Yes, ma'am.
Yes,
And
ma'am.
then when I say add A, data register's contents will be added to AC. Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes,
So
Ma'am.
effectively, this is what will happen. Effectively, A will be added to AC. Yes or no?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So the value of AC will change to 2.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, good. Now, what will happen when I say add B? Again, the same thing. B will be added to AC.
Yes, ma'am.
Yes,
So
ma'am.
now the value of AC becomes,
5.
we have our required sum now
Yes, ma'am.
in AC. Where do we have it? In AC. Okay. Now, please carefully see the next statement. I'm simply saying store in sum. Yes or no? Yes or no?
Yes,
I'm
ma'am.
saying store in sum. But what do I store in sum? I'm not saying. Automatically, the value of AC will be transferred to sum. Okay, its value will be transferred to sum. Okay, yes or no?
Yes, ma'am.
Yes,
So,
ma'am.
so this is how internally, even a single statement, a very simple statement such as sum is equal to A plus B, will be handled by uh, uh, one address register computer organization. Okay, if that means if we are only allowed to use a single address. Okay, so as I told you that we will be talking more about these organizations where we will see how to write down the same program in one using one address register organization and two address register organization and three address register organization. Okay.
excuse me, ma'am.
One second. Yes, tell me.
Ma'am, will the value will be deleted from
Yes, tell me, beta. Yeah, tell me. Who's this? Hello? Somebody wants to ask a question, you can. Please ask your question. Are you putting it in the chat? Because I cannot see chat. Since I'm working on the presentation.
Ma'am, am I audible?
Yes, you are. Who is this?
Ma'am, Pavitra.
Sorry, come again.
Pavitra.
Okay, Pavitra. Yeah, yeah. Tell
Ma'am,
me.
will the value will be deleted from AC when it is transferred to the sum?
No, 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 no. The value from AC does not get deleted. No. It doesn't get erased. It just gets copied there.
Okay,
Okay?
okay. Okay, ma'am. Thank you.
Okay. So this is clear to you how this is done?
Yes, ma'am. Yes.
Okay. So please see, this is the very basic format. Why I have taken one address register organization? Because this is the very basic kind of format of the instructions that we use internally. Okay, right? So what do you do? What do you see here is first a code for the operation which is to be performed. Yes or no? Isn't this a code for addition?
Yes, ma'am.
Yeah.
Yes, ma'am.
So here I've written add, but if I were to use machine language, I would have to give its code in binary. It's equivalent code in binary. Okay. So suppose let's say 1000100 represents addition and 0101 represents subtraction. Then I would have had to write this. This is how you would write in assembly language. This is how you are writing in assembly language. Okay. So in assembly language, you can write like this, but if this were in machine language, you would have had to write down the opcode. Opcode means the operation code. Okay. Opcode means the operation code in binary. Okay. The actual operation code, whichever value is associated with this particular operation in binary, and the address of the, not the variable name, but the address of this variable itself. Okay, in binary. Is this clear or not?
Yes, ma'am.
Okay. Right. So,
Excuse me, ma'am.
yes.
The address of A remains same, whatever the value is.
Yes. The address of A will remain the same throughout your program unless and until you're using pointers to explicitly change the address of A, which you have not learned up till now. Okay. So when your program, when your C++, I don't know whether you've done this in your C++ program class or not as yet. But whenever you start executing your program, C++ program, and your compiler, the assembler, after a program is compiled, after that it is assembled, and when it is assembled, then the actual storage spaces in the RAM are allocated to each variable. Okay, so at that time, these addresses are assigned to these variables. Okay, so when your program starts, memory locations, memory addresses, memory storage is assigned to these variables, and the same storage goes on till you actually exit the program. Okay, till you exit the program. That we call is it as the scope of that particular variable. That is the scope of this variable. That means till what time is it valid? It is valid till the end of your program. So once your program finishes, then these storage locations are made available. They are marked that they are free to be used by other programs. Clear?
Yes, ma'am.
Excuse me, ma'am.
Yes.
Ma'am, this is Chainika. I had a doubt
Yeah, tell me.
that if initially in the accumulator
Mhm.
the value was not 0, then what will we do?
So if the value was not 0 and we run these instructions directly without adding 0 to AC, then whatever, suppose it contained a value 100 initially, okay, then this would have resulted in the value 102. The first statement would have resulted in the value 102. then 105. So this would have been the final value, and this is what would have got stored in 10 in the sum. Okay.
Ma'am,
Yes or no?
so yes, ma'am, this is
So
understood. So
generally, this is what is generally done. Okay, so there are I'll be doing these instructions with you. I'll be doing these instructions with you. There are proper instructions corresponding to these statements that you will see later. For example, if I have to perform this task that load 0 into the AC, then we have a statement called LDA. We have a statement called, let me take another box here. So this is the first time I'm doing it on screen. Otherwise, you can do it on board. But I hope this is okay for you. I mean, not difficult to understand on PPT. Yes or no?
Yes, ma'am.
yes, ma'am.
I'm trying to, so these are the actual instructions that we will be doing later. Okay. The first instruction is LDA. It stands for load into AC. Okay, load into AC, whatever you want to load into AC. Suppose I want to load 0, then 0. Okay, then we say add A, add B, and then when we say STA sum, it means whatever value is there, automatically that goes and gets stored into sum. Is this okay?
Yes, ma'am.
Excuse me, ma'am.
Yeah.
Ma'am,
Tell
for
me.
multiplication, ma'am, for multiply, we will do sum is equal to 1 initially.
Yes, yes. If we had to multiply, we would have done sum is equal to 1 initially. Yes.
Okay, ma'am.
So in this case, however, you see, okay, let me not confuse you. Let it, yeah. Is this clear?
Yes, ma'am.
Yes, ma'am.
Okay. Is this clear to everybody?
Yes, ma'am.
Yes, ma'am.
So,
Yes, ma'am.
very good. So please see that, let us take one of these instructions and look more closely at it now. Okay, so what you are seeing on the screen right now, so let us say we are looking at this instruction add A. What is its format? So the first thing that you see here is I'm specifying a opcode. Yes or no? Opcode, I said, is the operation code, the code for operation. And then I'm specifying the address. To the computer, it is what? What is this to computer? This is just a address. What address? Address 200. Yes or no?
Yes, ma'am.
Can I hear a affirmation from everybody if you've understood this?
Yes, ma'am.
Yes, ma'am.
Good.
Yes,
Good.
ma'am. Yes, ma'am.
So you see that for the very basic instructions such as these, we automatically come to our basic instruction format, which is opcode and address. That means our instruction has two parts. One is the opcode and the other is address. But what is this? I can see another part of the instruction on the screen, isn't it? There is another part to it. This is called the mode bit. This is called the mode
Mode
bit.
bit.
Yeah. So what is this mode bit? This is going to be the discussion, the topic of discussion of our future classes. Okay. For the time being, I request you to accept it as a part of the instruction. Why this is required, why we have put this in, this I'll discuss with you later. Okay. Yes or no?
Yes,
Okay,
ma'am.
ma'am.
Yeah. So now let us try and reconnect this with something that we have already, discussed. Suppose we had a 4096 cross 16 memory, as in our basic computer we've already discussed, right? So what should be the total length of this instruction? This is what I want to ask you.
Sixteen. 16 bits.
It would be equal to the word length. We discussed this, remember?
Yes,
We
ma'am.
have discussed this, yes, because each location, this means that there are 4096 locations in my memory, and each location can store a maximum of 16 bits. So unless and until it is specified that one instruction is stored in 2 words or 3 words or 4 words, unless and until this is specified, it is assumed that one instruction is equal to 1 word of memory. Okay? Yes or no?
Yes, ma'am.
Yes, ma'am.
Can you repeat this? Who will repeat this? Chainika?
Ma'am, ma'am, it is like the instruction, all the instructions are stored in 16 bits until and unless it is mentioned that the instructions are to be stored in 2 words or more words. It is by default that one single instruction is stored in 1 word only.
Yes. Is this clear to everybody?
No, ma'am.
Beta, we have done this in the earlier class. If you remember, we had said that this means that there are these many addresses in this memory, and each address is capable of holding a maximum of 16 bits. This capacity of holding and manipulating 16 bits of information is called its word length. Okay. So in general, there's somebody asking me for a permission to join, but I'm already about to finish. So I am not letting them in. You can later, tell them this. Let me see who this is. So Soumya Gupta is joining, trying to join. I'm not allowing her. Okay. This is no time to join. It's almost an hour now. Yeah. So what we are simply trying to say here is that one instruction will be stored in 16 bits. Okay, that means 1 word of the memory. If I had said that one instruction is stored in 2 words of the memory, its length is equal to 2 words of a memory, then what would have been the length of the instruction? It would have been 32 bits. Okay, 4 words of the memory, then 64 bits. That means it would have taken, in case of 2 word length, it would have taken 2 locations to store one instruction. But let's not go there at this time. Okay, let's keep the things simple for us. So right now, since nothing has been said, we assume that one instruction length is equal to 16 bits. Okay. So
Yes, ma'am.
I'll stop here for the moment, and next time we'll take it forward from here. Okay, we will take it forward from here. There are a couple of examples from your book as well, which I've taken, which I'll do in the next class. So I'll do them in continuation. Okay, so that's why I'm stopping here for the day. After that, the roadmap for the next class would be that we will be discussing the types of instructions, and then looking at each of these instructions in particular. I will be introducing you to this mode bit that we have talked about. Why is this required? And the different opcodes which have been reserved for each memory, for each type of instruction. Okay, so this is what we will be doing in the next lab class. Okay, I'll stop here for the minutes and I'll circulate the attendance. Please mark your attendance.
Excuse me, ma'am.
Just a second. Yes, tell me.